Good day. For those of you who do not know us, we are the instructional staff for ECE 150. Professors Hiren Patel and Werner Dietl and Douglas Harder. In this topic, we're going to look at break statements. So in this lesson, we will introduce the concept of breaking out of a loop prior to the condition returning false. We will take a look at a previous example and see how this can be used to get a solution faster, and then we'll look at a few other examples as well as looking at how to break out of nested loops. Consider this program which we've seen previously that determines if an integer n is prime. It does so by checking if it's divisible by 2 and then checking whether or not it is divisible by any larger odd number. If it is prime, we will state it is, otherwise we will indicate that it is not prime. Now, suppose we use this program to determine if 303 is prime. Well, first, the remainder modulo 2 is equal to 1, so it doesn't tell us anything, but 303 mod 3 is equal to 0, so 303 is indeed divisible by 3. However, our program would continue to test if 303 is divisible by every other odd number all the way up to 301. But wait a second. After k equals 3, we're done because we already know that 303 is not prime at this point. So why are we testing all other numbers? This allows us to introduce the break statement, which allows us to terminate a loop early. A break statement appears by itself as a separate statement, and as soon as the break statement is executed, the loop immediately stops. The condition is not tested, no other statements are executed, the update statement is not executed. Basically, in this case, if we ever determine that n is not prime, we will set is prime is equal to false and then issue a break statement. At this point, as soon as the break statement is executed, the loop terminates and execution continues where indicated here. So even though the condition is still true, the loop stops executing. This is useful because once we've determined that n is divisible by any number, we no longer have to run any tests because we know that n is no longer prime. Alright, the problem here with this test, however, is we're still doing a lot of work, especially if n is prime. If n is prime, we are testing whether or not n is divisible by every single odd integer up until n minus 1. Now, consider the following. Let's say that n is not prime. If n is equal to the product of two integers, m1 and m2, then one of these two conditions must be true. If n is a perfect square, it may be that n1 equals n2 equals the square root of n. The alternative is that if m1 is less than the square root of n, then m2 must be greater than the square root of n. So for example, the square root of 420 is approximately 20.5. 420 is the product of each of these pairs of integers. And in every single case, including 20 times 21, one of the numbers is less than the square root of 420, the other one is greater than that number. What that means is if we've already tested, for example, if 420 is divisible by 10, we no longer have to test if 420 is divisible by 42, because we would have already found that out when we divided 420 by 10. Thus, we can improve our program. So initially, if we found that n was divisible by k, then we set is prime is equal to false, and we break, as we've now determined that n is no longer prime. However, if k times k is greater than n, that means that k must be greater than the square root of n, and therefore we have already tested every single integer up to the square root of n to see if n is divisible by that integer. And since none of them were divisible, then n must still be prime, and there's nothing else to test. So if k times k is greater than n, we will just issue a break statement, and the for loop is done because we have determined that yes, indeed, n is prime. Let's consider the benefits of ending this loop early. Previously, if we were to test whether or not a number that was approximately 1 million in size to see whether or not it was prime, we would have had to test every odd number for divisibility up until n minus 1, meaning we would have had to find the remainder for approximately 500,000 numbers. Now we only have to test odd numbers up until the square root of 1 million, which is we only have to test all odd numbers up until 1,000, which is approximately 500 numbers. That's a lot less work than testing 500,000. Similarly, if we were to test if a number that was approximately 100 million in size to see whether or not it was prime, previously we would have had to find the remainder of that number for 50 million odd numbers. Now we only have to test all odd numbers up until the square root of approximately 100 million, which is 10,000, and so we're only going to have to find the remainder for approximately 5,000 odd numbers. That's a lot less work. Even if you were able to find the remainder at the rate of 1 million per second, originally this would have taken 50 seconds, versus now it will take 5 milliseconds. Now, here's a simple observation. We really didn't need the break statement here, although I think it was very clear as to what the break statement was doing. However, we could have incorporated each of these conditions into the for loop itself. So for example, here I have modified the condition to not be as long as k is less than n, but instead I'm testing so long as is prime is true and k times k is less than or equal to n. If either of these conditions is false, then the loop terminates. Now, previously we added 2 conditional statements. Here I've incorporated those conditions into the for loop condition. Both of these are completely acceptable, and you are always welcome to do one or the other as you see most fit. Technically, you never actually need a break statement, but using a break statement is often very convenient and also clear. Next, in discrete mathematics, a course you will be taking next term, a very useful calculation is the integer square root. The integer square root of an integer n is the largest integer m such that m squared is less than or equal to n. Now, if n is a perfect square, then n is equal to m squared for some integer m, and therefore the integer square root is that square root value m. For example, 10 squared is equal to 100, therefore the integer square root of 100 is still 10. However, consider 99. 99 squared is 81, which is less than 99. 10 squared is equal to 100, which is greater than 99. Therefore, the integer square root of 99 is 9. Now, consider this program, which finds the integer square root of a given integer n. What we do here is we initialize a local variable I square root to be equal to 0, and then we have a for loop. That for loop runs from m equals 1 up until m equals n minus 1. Every single time the loop runs, I will test, is m squared less than or equal to n, and if so, I will update the value of I square root. Because m is getting larger with every single iteration of the loop, therefore the final value assigned to I square root will be the largest integer such that m times m is less than or equal to n. And so therefore I can print that value once the loop terminates. Now, one problem with this program is that we're testing a lot of integers. Specifically, we're testing every single integer up until n minus 1, even if the integer square root is much smaller. For example, if we were to use this loop to find the integer square root of 1 million, which is 1,000, we would still be testing 999,999 integers. That's a lot of work. Now, what happens if m squared is less than or equal to m, n is false? Well, if that statement is false, then m squared must be greater than n. But if m squared is greater than n, then m plus 1 all squared is also greater than n, in which case every number greater than or equal to the current value of m must also be greater than n, and therefore none of those integers can be the integer square root. In other words, if the condition of the conditional statement we see here is false, then we're done. We have found the integer square root. Thus, we can significantly reduce the amount of work by simply including an alternative block that breaks from this for loop. So for example, if we were finding the integer square root of 1 million, once m was equal to 1,000, 1,000 times 1,000 is still less than or equal to 1 million, so we would update the local variable I square root. With the next iteration of the loop, m is equal to 1001. 1001 squared is greater than 1 million, and so therefore the condition fails, and we would end up in the alternative clause, which would break out of the loop. This would significantly reduce our work from checking almost 1 million integers down to checking 1,001 integers. Now later in this course, we're going to see an even faster mechanism or algorithm for finding the integer square root of a given integer. Suppose we want to find if n is the sum of two non-zero squares. That is n equal to m1 squared plus m2 squared for two non-zero integers m1 and m2. Now, in engineering, very often we don't need to find all possible solutions. We only have to find one solution if it exists. So as soon as we find one pair of integers such that the sum of the squares of those two integers is equal to n, we're finished. Now consider this program that attempts to determine whether or not a given integer n is the sum of two squares. First, we will set a Boolean local variable is found with the initial value false. What we will then do is test whether or not n is equal to m1 squared plus m2 squared for all values of m1 and m2 running between 1 and n minus 1. So here we have an outer for loop where m1 takes on all values between 1 and n minus 1, and each time the outer loop is run, the inner loop has m2 taking on all values between 1 and n minus 1. If we ever find that m1 squared plus m2 squared does indeed equal n, then we will set the local variable is found is equal to true and exit the loop. Well, not really, but at this point we do have a problem, because once we exit the loop, remember that the scope of m1 and m2 are restricted to these two loops. Therefore, those two local variables are gone or out of scope once these loops exit. So how do we know what m1 and m2 are? Therefore, if we want m1 and m2 to be in scope, even though we're outside of the two for loops, we must declare m1 and m2 to be local variables of the function main, and then we can test all pairs of integers m1 and m2 running between 1 and n minus 1. If m1 squared plus m2 squared is ever equal to n, we will then indicate is found is assigned the value true and break. Now, thus, once the loops exit, we will check if is found is set to true, then we will print that n is equal to the sum of the squares of those two integers. Otherwise, we will indicate that n is not the sum of two non-zero squares. Let's try running our program. The program asks us to enter an integer. Suppose we enter 121. Now 121 is equal to 11 squared, but it turns out that 121 is not the sum of two non-zero squares. So the program correctly gives us that output. Suppose we run the program again. However, this time we enter 122. Well, you should realize that 122 is equal to 121, which is 11 squared, plus 1, which is 1 squared. So 122 is 1 squared plus 11 squared. So that's what we expect to see in the output. However, the program prints out the following. 122 is equal to 122 squared plus 122 squared? No, it's not. What happened here? The problem is the break statement only exits from the loop in which it is found, which in this case is the inner loop. So when this break statement is executed, it simply jumps to the point indicated here. But that point is still inside the outer for loop, so the outer for loop will keep on running, subsequently incrementing the value of n1 and re-executing the inner loop. Now, you'll recall that m1 and m2 were declared local variables with their default value of 0, and isFound was declared a local variable of type bool with the initial value false. The outer loop runs. m1 is assigned the value 1, and now we run the inner loop. m2 is assigned the value 1. We now check the condition. Well, 1 squared plus 1 squared is not equal to 122, so The condition is false, so we increment m2. The condition is still false, so we increment the value of m2. The condition is false, we increment the value of m2. The condition continues to be false up until m2 is assigned the value 11. Now, m1 squared plus m2 squared is equal to 122, so we set the condition is true, and we set is found is equal to true, and we execute the break statement. But that only jumps out of the inner for loop. We're still in the outer for loop, so at the end of the outer for loop, m1 is incremented, and now we re-execute the inner for loop. m2 is equal to 1, and so on and so forth. However, all this time now is assigned the value true. So the inner loop and the outer loop will keep on executing until m1 equals 122 and m2 equals 122, and that gives us the reason we see the output that we previously saw. The solution is that once we finish executing the inner for loop, we check. Did we find a pair of integers that satisfied our condition? If so, we should break out of the outer loop as well. Easy enough. And if we implement this and run our program, now with this correction, let's try running our program again. Enter an integer. We enter 122, and the output is, yes, 122 is equal to 1 squared plus 11 squared. And we're done. Thus, following this lesson, you now understand the purpose of a break statement. Its purpose is to end the current execution of a for loop. In fact, a break statement can only appear inside a loop. You also know that the break statement is simply the keyword break followed by a semicolon. You understand how to finish a loop through a number of examples if it is determined there is no longer a need to continue executing a loop. However, it only jumps out of the loop in which it is found.